Good morning everyone. Welcome back to analysis of indeterminate structures. In this session, let us consider a simple continuous beam subjected to point load and UDL as shown in figure. And we are going to solve this particular continuous beam by using flexibility matrix method. So, as we discussed in the previous session, so we know the flexibility relation is given as matrix D equals to matrix F into matrix P. And you all know matrix D is the column matrix which is having the order n cross 1, and also matrix P is a column matrix having the order n cross 1, and matrix F is a square matrix having the order n cross n, and D is nothing but displacement matrix, F is nothing but flexibility matrix, and P is a force matrix. So, this relation forms the basis for flexibility matrix approach. So, let us call this as equation number 1. We have very simple steps to be followed to analyze this particular continuous beam. Let us take the step number 1. So, here step number 1 is to find the degree of static indeterminacy. So, after finding degree of static indeterminacy, based on the number of static indeterminacy, we need to assume the redundants. Redundants are nothing but unknown forces which may be in the form of reactions or moments. Then we need to mark the moments on this indeterminate structure. After assuming the redundants, we need to mark the coordinate directions. So, let us find the degree of static indeterminacy. The degree of static indeterminacy is given by number of unknown forces minus number of known equilibrium conditions or known equilibrium forces. So, here if you observe the beam, so we have 3 supports. So, at A we have fixed support which is having the unknown reactions in the form of, we have 3 unknown reactions here. One is vertical, another one is horizontal, and another one is moment. If you come at B, so we have one vertical unknown reaction here. Again coming to the C, it is also a roller support, therefore again we have one unknown vertical reaction there. As we know, in beams we won't consider the axial forces. So, you can neglect the horizontal force in case of beams. So, if you count the number of unknown reactions in the given beam, we have 1, 2, this is 3 and 4. So, number of unknown forces will be equals to 4 minus number of known equilibrium conditions will be 2. Here, since we neglect the horizontal equilibrium condition, we will get summation of Fy equals to 0 and summation of Mz equals to 0. If you consider these two equilibrium conditions, it is enough in case of beams. So, it equals to 2, number of equilibrium conditions 1 and 2. Therefore, degree of static indeterminacy for this particular beam will be 2. So, based on this number, we can fix the order of flexibility matrix. So, if you get 2 here, the order of flexibility matrix will be 2 cross 2. If you get 3, this will be 3 cross 3. So, in step number 1, next we need to mark the redundant forces. That means we need to assume the redundant forces. Here we need to assume 2 redundant forces. So, we can mark reactions as redundants or moments as redundants. So, in this particular beam, let us select moments as redundants. So, here the unknown moments will be at A, that is MA, and at B, that is MB. Of course, at C, since it is a roller support, moment at C will be equals to 0. So, let us mark the redundants on this particular beam. Let us call the given beam as figure A. Assume MA and MB as redundants. Therefore, the released structure will be the two independent simply supported beam AB and BC along with the redundants as shown in figure B. Okay, this is A, this is B. Since B is the intermediate support, we can split the structure like this. So, as you all know, this is 60 kilonewton and this is 10 kilonewton per meter, and here we can mark the redundants like this. This is MA and here we can have MB. So, this is called, let us call this as figure B. So, determinant structure. Now, we should select, after marking the redundants, we should select the coordinate directions. So, here we can have the general coordinates along the direction of assumed redundants. So, call this as coordinate number 1 along MA, call this as coordinate number 2 along MB. After assuming the redundants, next we need to mark the coordinates along the assumed directions of redundants. Since we have two numbers of unknown forces, that is static indeterminacies, we get two coordinate directions here. coordinate number 1 will be along the direction of MA and coordinate number 2 will be along the direction of MB. So, this completes step number 1. So, what we do in step number 1? So, we find degree of static indeterminacies. Based on that, we assume the redundants which may be in the form of reactions or moments. Then, along the direction of assumed redundants, we should mark the coordinates. So, in step number 2, we should sketch the bending moment diagram and the corresponding conjugate beam to find the displacements along the coordinate directions due to the applied loading conditions. So, let us draw the bending moment diagram for this released determinate structure. So, for span AB, since we have point load here, we have the bending moment diagram in the triangular pattern. Clear? So, and for span BC, since we have UDL, we all know for uniformly distributed loading condition, we have bending moment diagram in the shape of parabola. Clear? So, now, this value can be find out by applying the formula WL by 4, and here we have WL square by 8, and you all know at supports the values are 0. So, this is the real beam and we are writing the bending moment diagram. So, this is WL by 4 means 60 into 6 divided by 4, and we'll get the value like 90 kilonewton meter, and here it is 10 into 6 square divided by 8, and we'll get the value like 45 kilonewton meter. So, this is called figure D. This is a given bending moment diagram for this particular loading condition. So, now let us sketch the conjugate beam. That means we need to load this bending moment values on EI diagram. So, that gives us the conjugate beam. So, you know simple supports remain as simple supports in conjugate beam. Therefore, A support, that is at A, at B and at C we have simple supports. Therefore, in conjugate beam also the support remains as it is. So, if we load the diagram on EI, so we have the conjugate beam. Since we have the positive bending moment, the loading direction in the conjugate beam will be in the downward direction. Clear? And this value will be 90 by EI, and here we have 45 by EI, and let us call, so since it is A, so that in conjugate beam let us call this as A dash and this as B dash and this support as C dash. So, this will be figure E, and this is called as conjugate beam. Clear? So, this is the real beam, the determinate structure. So, this is the real beam and this is the conjugate beam. So now at supports we'll get the reactions like this: RA dash, RB dash and RC dash. So this forms the step number 2. In step number 2, we sketch the bending moment diagram and conjugate beam based on the given support conditions and loading diagram. Next we have step number 3. In step number 3, we are going to find the displacement matrix called DL. And we know the order of this displacement matrix is 2 cross 1. This will be the column matrix. So this displacement matrix will be in the form D1L and D2L. So here DL is nothing but displacement at the assumed coordinates due to the application of loads. So here D1L represents displacement at coordinate number 1 and D2L represents displacement at coordinate number 2 due to the applied loading conditions. Since we are using the concepts of conjugate beam, you all know if you want to know the displacement, since we are applying moments, we'll get the displacement in the form of slope, that is theta. Since moment is the unknown force here, the displacement will be in the form of slope. To get the slope at this particular points, that means to find the slope at A, we need to find the shear force at A dash. That means in real beam we require theta, in conjugate beam we should find shear force. So here D1L is nothing but theta A and D2L is nothing but theta B. So next we need to find out this theta A and theta B by using the conjugate beam. In previous semester you have learnt the conjugate beam method. By using those concepts, now we shall find out theta A and theta B. So from the conjugate beam concepts, theta A in real beam equals to shear force in conjugate beam. So shear force at A dash. Clear? And if you want theta B, you should find out shear force at B dash. Clear? So shear force at A dash is nothing but RA dash. So this equals to RA dash, and shear force at B dash is nothing but RB dash from span AB and also from span BC. So here we get RB dash plus RB dash. So this is from span AB and this is from span BC. So let us find the reactions. So how to find these reactions? So we can find the reactions RA dash, RB dash and RC dash by applying simple equilibrium conditions. So let us take the span AB. From span AB, we can have RA dash equals to RB dash equals to, since we have symmetrical triangular loading, we can have total load divided by 2. So total load here is half into base into height is 90 by EI, this is the total load, whole divided by 2, and by solving this equation we'll get the answer like 135 by EI. So this is for span AB. Next we have from span BC, RB dash equals to RC dash equals to, and since again we have symmetrical parabolic loading here, so it is the total load will be given by 2 by 3 of span, that is 6, into height is 45 by EI divided by 2. It is 90 by EI. So now we have already formulated the relation. So we want theta A. Theta A is nothing but displacement at coordinate number 1 due to the applied load. So since we want theta A in real beam, we should find the shear force in conjugate beam. Therefore, shear force at A dash will be RA dash, and we have got the value of RA dash as 135 by EI. Next we have theta B, so that is the shear force at B dash. So since B dash is the common support for both the spans AB and BC, so we should find the RB dash for AB span and BC span. So we have got the answers like for AB span, RB dash value is 135 by EI, and for BC span the RB dash value will be 90 by EI. So by solving this equation, we'll get the final answer for theta B as 225 by EI. So thus we got the DL matrix. So if we take out 1 by EI outside, so theta A will be 135 and theta B will be 225. Next we have step number 4. So here we shall find the flexibility matrix which is having the order 2 cross 2. So here in flexibility matrix we are going to find out the flexibility coefficients called F11, F21, F12 and F22. And we are going to find out the flexibility coefficients column wise. So here, so in general we can call Fij. So ith column represents displacement and jth column represents the force along the coordinates. So here we are going to apply the unit forces along the coordinates number 1 and 2, and we shall find the respective displacement along the coordinates 1 and 2. For example, if you consider the first column of F matrix, we are going to apply the unit force at coordinate number 1 and we check the displacement developed at the coordinate number 1 and the coordinate number 2. In the same manner, for the second column, we are going to apply the unit force along the coordinate number 2 and we check the displacement developed at coordinate number 1 and 2. So this jth column represents the force we are going to apply and ith column represents the displacement developed at the particular coordinates we have assumed. So to find the first column elements, we should apply unit couple along the coordinate number 1 as shown in figure F. So we have this is A, B and C. This is also 6 meter. This is also 6 meters. We know at A we have coordinate number 1. So this is coordinate number 1 and we are going to apply unit couple, that is unit moment at coordinate number 1. This is figure F. So this is unit couple at coordinate number 1. So then we need to draw bending moment diagram for this particular beam and we need to load that bending moment diagram on EI diagram to get the M by EI diagram, and then we treat that M by EI diagram as conjugate beam. So if you draw the M by EI diagram, as usual the span and support conditions remain as it is. So that means in real beam we have simple supports. So in conjugate beam also simple support remains simple support. That means in real beam we have simple support. In conjugate beam also we get simple supports. Then here we have 1 by EI and at this end it will be 0. Since we have positive bending moment, the loading condition will be in downward direction at B dash, and we can call this as A dash, this is B dash, this is also B dash and C dash. So this is called figure G and this is called conjugate beam. So here we need to find the reactions, that is RA dash, RB dash for span AB and also for span BC we need to find out RB dash and RC dash. Just like displacement matrix, we need to find the shear forces in the conjugate beam. So if you find the shear forces in the conjugate beam, we can get to know the displacement developed in the real beam. That means here the coefficients F11 equals to theta A. So that is nothing but shear force at RA dash. Then F21 equals to theta B. So that is the shear force developed at RB dash. So here we should find out RB dash from both the spans AB and BC. Clear? So you all know F11 is the displacement developed at coordinate number 1 due to the application of load at coordinate number 1. This is the displacement developed at coordinate number 2 due to the applied load at coordinate number 1. Here the load applied is 1 kilonewton meter. So while applying unit couple at coordinate 1 and 2, we should remove all other kind of loadings. Clear? Let us find RA dash and RB dash. So from span AB, if you take span AB, RA dash equals to, you can apply the moment equilibrium conditions and force equilibrium condition, or else you can find RA dash like this also. So RA dash equals to half into base is 6 meters into height is 1 by EI multiplied by, since I need RA dash, multiply this loading by 2/3. So by solving this equation, we'll get the answer like 2 by EI. So if you want RB dash, so do the same thing, half into base into height, the loading condition multiplied by, since you need RB dash, multiply the load by 1/3 of the span. So if you solve this, you'll get the answer like 1 by EI. So in the same manner, if you find RB dash and RC dash from span BC, RB dash equals to 0 and RC dash is also equals to 0, because we don't have any sort of loading on this particular span. So now if you write here, so F11 is nothing but theta A, so that is equals to 2 by EI, and F21 is 1 by EI plus 0, so that is equals to 1 by EI. So we got the first column elements in the flexibility matrix. In the same manner, we are going to find the second column elements, that is F12 and F22. That is, we are going to apply unit couple along the coordinate number 2. So as I said, to get the second column elements, we need to apply the unit couple along the coordinate number 2. So this is coordinate number 2. So here we are going to apply the unit couple, and we are going to generate the conjugate beam. So if you apply the unit couple here, so as usual the support and span remains as it is. This is A dash, this is B dash, this is C dash, this will be RA dash, and this is RB dash, this is also RB dash, and this is RC dash. This is figure I, this is a conjugate beam, and here we have 1 by EI. So to get the second column elements, we need to apply the unit couple along the coordinate number 2 as shown in this figure, and after sketching the bending moment diagram, we shall load that bending moment diagram on EI diagram to get the conjugate beam like this. Clear? So for this kind of loading arrangement, we get the bending moment diagram in the right angle triangle pattern. So the bending moment value divided by EI gives the M by EI diagram, and this forms the conjugate beam. Therefore here figure I is the conjugate beam. So now to get the second column elements like F12 and F22, so the displacement at coordinate number 1 is nothing but theta A, and the displacement at coordinate number 2 is theta B. So at A, if you want theta A, I need to find out RA dash, and if you want theta B, I need to find out RB dash from both the spans. So let us take the first span AB. So there RA dash, again write the load, half into base into height is 1 by EI. I want RA dash, therefore just multiply this load by 1 by 3. So this equals to 1 by EI. So if you want to find out the RB dash, clear? So again take the load, half into base into height multiplied by 2 by 3. So this gives you 2 by EI. So again from span BC, if you want to find out the RB dash, again it is half into base into height, so multiplied by 2 by 3, so I'll get 2 by EI, and half into base into height multiplied by 1 by 3, I'll get 1 by EI. So if you solve here, RA dash from span AB, it is 1 by EI, and RB dash from span AB and BC we have 2 by EI plus 2 by EI. So the final answer is 4 by EI. So now we got all the 4 elements in the flexibility matrix. So take out 1 by EI as common. So I'll get F11 is 2, F11 is 2 and F21 is 1, and F12 is 1 and this is 4. So this completes the step number 4. So next we have step number 5. Step number 5 is to find out the P matrix. Again this is in the order of 2 cross 1. We have P1 and P2. So P1 is nothing but the force at coordinate number 1, that is MA, and P2 is the force at coordinate number 2, that is MB. And we all know the basic flexibility relation is given as D equals to F into P, and this D can be written as D minus DL equals to F into P. In previous session I have explained this. Clear? So here this D matrix is equals to 0. That means here the D matrix represents the final displacement due to the reasons like sinking at the support or rotation at the supports. Since in the given problem we don't have such conditions, this D matrix equals to 0. So if you solve this equation, we will get minus DL equals to F into P. Correct? So I need to find out this P. Therefore, so if you substitute the values, so we already solved for DL matrix. The values of DL matrix are, so minus outside 1 by EI into D1L is 135 and D2L is 225, and here F matrix is 1 by EI is common, it is 2, 1, 1 and 4, and this is P1 and P2. So EI and EI gets cancelled. So if you take this minus into the inside, so you have minus 135 and minus 225. I want P matrix. So on rearranging this equation, P1 and P2 equals to F inverse. So this will be the inverse into, clear, minus 135 minus 225. Clear? So like this you have to solve the equation. D minus, if they give rotations or sinking at the supports, you get the values for this D, or else this D will be 0. And we have DL based on the loading conditions. So by solving the equation, we can find the P1 and P2. We can solve this particular equation with the help of calculator, or else you can solve manually. You know how to take the inverse of 2 cross 2 matrix. So on solving this equation, see, manually we can have P1 and P2 equals to, see, manually to remove this inverse, we should have determinant of this matrix as 2 4s are 8, minus 1 it is 7, 1 by determinant, and just interchange the diagonal values and put the negative sign for this particular diagonal elements. Now minus 135 and minus 225. So if you solve this, see, you can easily multiply this. This is 2 cross 2 and this is 2 cross 1. We are going to get 2 cross 1 matrix. So it is 1 by 7 into 4 into minus 135 plus minus 1 into minus 225, then minus 1 into minus 135 plus 2 into minus 225. So if we solve this, we will get P1 and P2, that is P1 and P2 is nothing but MA and MB, that is equals to minus 45 and minus 45 for both P1 and P2. Therefore, here MA is minus 45 kilonewton meter and MB is also minus 45 kilonewton meter. So we got the values for the marked unknown redundants. So we have got the negative sign, that means in our original beam, see, this is our beam, 60 kilonewton. This is A, this is B and C. So we have marked this as MA and this as MB, correct? So here, after getting the final values, since we have got the final values in the negative manner, so you can either change the direction or you can write the values along with the negative sign. I am going to change the direction. So this is 45 kilonewton meter. So here also I am going to change the direction. So I am changing the direction because I have got the negative value. So if you got the positive values, you need not to change the direction. You just write the values as it is for the assumed direction. So this completes the analysis of the simple continuous beam by using flexibility matrix. In all the problems, we use these simple 5 steps to solve the problem. And yes, we need to draw shear force and bending moment diagram for this particular beam. So that you have learnt in your previous modules. Yes, I am going to explain how to draw shear force and bending moment diagram in my next session by taking another simple continuous beam. Thank you.